Hello and welcome to Embedded Internals. This is first episode of our series C System Fundamental series. Why C still rules system programming. System programming language which is very close to hardware, and that is the reason it is dominating the world and will continue to dominate the world. Mastering the C programming language doesn't mean just mastering a language. It means that you are understanding the operation of the operating system from the high level, from writing the code and how it is getting executed at the hardware level. So we have a program to add two variables. Okay, so this is a very small program too, where we have one variable x in which we have stored the value 5, and at the next statement we are adding 3 to 5 and storing the result into the same registers, printing the value of x. Correct output. Output is x. So this is not our object goal. Our object goal is how the machine is interrupting this program. So when you say this program, simple program at the assembly language, is such a huge code. Reading from the file format, ELF file. We have a init section, ENDBR64. This is an flow control enforcement technology which we are using in a 64-bit mode, and it is like 86 instructions to terminate an indirect branch in 64 mode. So its purpose is to serve as landing pad for indirect branches. Okay, so this is the target marker. Our SP is our stack pointer, RIP is our instruction pointers, and these are registers, AX registers, base registers, and all these things. We are testing the registers, calling. So these all are PLT sections. And finally, this is where our program is getting started. In our execution awareness series, we have declared how we get this address 1060, how we know that what is underscore start in the episode where we are declaring what happens before the main function. Please do check out that. So this is the where our program starts. So this is our landing pad for indirect branches or calls or jump. We have two registers, we are moving some value, we have stack pointers, SISP, these exhaust, calling the main function. So this is where finally from the kernel level we are moving to our program level. So this main function will be called from libc library. Libc start main is will call main function. So main is 1149. So when you see the address we are getting for main is 1149. So it is telling to go back to this address. So we reach to the main 1149. So this is our main function. This is our launching pad. So we are pushing the base pointer into the stack, and we are moving the base pointer and the stack pointer. The whole complete stack is being controlled by these two pointers only, where stack pointer is tracking the current location, whereas base pointer is pointing to the base location inside the stack. So this from this instruction we are allocating the stack memory. So it is like subtract 16 decimal from the stack pointer, which means as stack grows downward in memory, so this will allocate 16 bytes of stack memory to hold local variables, function arguments, return types, data structure, anything. So we are allocating the memory here. So moving 5 into the base pointer. So 4 bytes, integer is 4. So 4 for the 5, and then in this value we are just adding 3, and then moving this address to our AX register, and then register to the stack pointer, so that we have to jump back to the instruction pointer. And this is how we are doing. Null pointer means we have to leaving the stack and calling the printf function to print the values, leaving this main function, and finally returning. So printf will be called, this is to call printf 1050. There is 1050 in printf statement. So it is jumping to the instruction point address and printing the value of whatever is stored in RAX and then returning. So all these are happening for our small program to add two variables inside the assembly code. If you have covered our execution awareness series, all the 10 episodes, then it will be easy for you to understand this assembly programming. So we have seen that C maps extremely closely to machine instructions. So we have seen our stack allocating 16 bytes, means 4 4 4 4 for the values. So when we are adding 5, a stack variable will be used. C stack variable will be used. When we are returning, this will popped out, this will be popped out. So initially the base pointer and stack pointer will be here if it points to the top of the memory location. When we have allocated the memory 16 bytes, so stack pointer will move here. When any new variable is adding this, whatever will be the stack, the top of the stack pointer will points to that. Whenever the value got popped out, stack pointer will move. So this is the moving pointer and this is the stable base. From this we can calculate the stacks operation. So stack is going downward, so we have allocated 10 into 6 into, we are whenever we are allocating the memory, you are saying minus sign, so move downward into the memory location. Okay, so this is how C is mapping CPU, memory and instructions together. So now, okay, why high level language exists? We have seen the assembly language. Understanding it is difficult, and when we have to write the program in this way, how difficult or how painful it is going to be. So our third topic is why high level language exists. We have seen the assembly code of our program. It will be very difficult for us to write the code in this way. That is why we need some simpler form of language where we can easily create the logic and let the computer or let the machine do all the translation. I have one simple code to increment a two variable. Like when you have to increment a value, like x is initially 10, you want x to be incremented by 1. So simply x plus 1, or this will become x is equal to x plus 1, or you can do x plus plus, use the increment operator. So this will be such a simple code. You will declare a variable, store some value and do the incrementation. So this is a 2-line code. Okay, what will happen when you have to write this program in assembly language? You need a proper understanding of all the registers, all the jump instructions, all the addresses. So let me show you one simple example of this in assembly language. So I have declared text segment global start, it will be the main function. This is the stack frame which I am setting. So push RB, the base pointer, move the base pointer into the stack pointer and allocate the address for the stack. Here we are declaring one variable. In this register, declare a variable having the value 100. Okay, now move EX into this register, add 1. So now the value will be moved into EX register and we are adding, incrementing by 1, and then that incremented value is being stored in the EX register. moving to the sixth as exit and doing the exit. Let us compile this. As this is an assembly language code, we will use NASM to compile it. This is the instruction, NASM hyphen ELF64 this, and the object file generated is this. We have to load this object file now. And after linking the value stored, give the ELF. So ELF will be INC, this one. So when you run the ELF, you didn't get the output. So to read the output, you have to use the shell operation. Output is 101. We have 100 stored in the x variable and we have added 1. So it is 101. So this is the output. So this is how this is what will happen when you have to write the code into the assembly language. Why high level language exists? We have seen the code in the assembly language and we see that writing assembly code is so painful. All the code which is written in the assembly language is architecture specific. So we have to be very specific about the architecture we are using. It can be x86 architecture, ARM architecture, that it can also be 32 bits or 64 bits because we are directly dealing with the registers. So writing assembly code is not only painful but it eventually become very unreadable. As it is unreadable, it is very hard to maintain and easy to break. Debugging assembly language code is very hard. Eventually we have to rewrite the code or it will be easy, very easy for the break. Like when we are writing, as we have seen in our example increment.c, to increment one variable we have to move the value we have to store that value in our register, base pointer register, and move that value into our ex register at increment and then move the result back to the ex register. So this is not just a increment operation, whereas to reach this operation we have lots of other operation like uh, taking the stack, store allocating the stack, allocating all the frames, all the stack pointers, base pointers, allocating the section for the text segment, local segment, everything. So it is very easy and very difficult. So it is very difficult and painful to write code in assembly. Whereas when we are doing the same thing, increment in C, so it will just a one statement, x plus plus. So you are incrementing. So we can say that what C provide is, C is not any architecture dependent, so C provide the portability. It is very easy to read and understand the code, so we can say C is a very readable language and it provides an abstractions. There is also a hiding, it is also, this statement is also hiding lots of things, but still it is not hiding the machine too much. So it is creating a balance between what to hide and what not to hide. So even if it is hiding, it is still, it is not hiding much of the machine. So that balance is the reason C is still dominating and will continue to dominate. So it is close to the machine and close to the user. When we say where C fits, we have seen when we do the programming from upper to lower level, whenever you write any code, we can say that is as an application. Code can be in any language, whatever is you are friendly into, C, Python, Java, C++, or many languages. It will eventually calls the library. Library can be glibc library and other libraries for other languages, and that will call the, if that is a very high level language, Pythons, Java, they will call the interpreter, which is eventually in C. And then the libraries call will finally needs the kernel, operating system help so that they can execute. So when the user is accessing the or asking the operating system to do their task, we can say that operating system is executing on the behalf of a process, so it is in the process context mode. So library eventually enters using system calls. Once is enter the kernel. So this is C, this is C. Kernel will eventually call the device drivers. Like when we have to print one statement, we are calling the terminal driver. Every driver is eventually in hardware, so firmwares that will call the hardwares. We are reaching at the registers level. So all the lower level is dominating by the C. Application can be in any language, but hardware is in, drivers is in, kernel is in C. C is dominating lower levels. Why it is dominating? Because it has predictable memory layout. We have a dedicated, so C is providing direct hardware access using memory mapped IOs. So we are so hardware registers are directly mapped inside our memory. So registers become the memory which we can easily read, write and do the operations. As C is very close to hardware, it has tiny runtime and very near assembly performance. Now the next topic is C versus assembly. Although we have already seen, when you are writing the code into the assembly, we have maximum control. When we say maximum control, we are controlling directly our registers. We are the one who is deciding how much memory need to be allocated, where the stack pointers are currently are. So we have memory stack pointer, base pointer, instructions pointer, where we need to jump, when to return. Everything is being controlled by the programmer. So assembly language is giving the maximum control it can give to the programmer. But this is pros. When we say what's the problem we are facing, so it is non-portable. We have already seen it is architecture specific. So we cannot port on one architecture dependent code onto the other. See, it is non-portable. Huge development cost. Performance is good once a code is written. So performance is good, but development cost is very high. Very difficult to write, very difficult to maintain, and very easy to break. So development cost is very high. Whereas when you are writing the in C, C is portable. So no architecture dependence. C is very fast, close to hardware, so it is very fast. Low level programming language, so you have the understanding from the whole operating system to the hardwares. It is very expressive and compiler optimized, already optimized for the compiler, along with better memory layout, memory control, hardware and registers control. C gives lots of portability pros. So whereas C also have some problem like it is little difficult as compared to other high level programming languages like Python and Java. C is difficult. But once you understand C, you understand the operating system. So next topic is how the C source code become executable. Just a reminder to check out our execution awareness series where all the 10 episodes are on this topic only, how source code is becoming the executable. What is happening when at the compilation stage, what are ELF, how we can read the ELF, what happens before the main function, what is the printf pipelines, what are user space, kernel space, how we can debug everything is inside our execution awareness series. Do check out. Let's come back to our topic, C source to executable. When you write .c program, so .c, your source code will go through preprocessor and we will get .i where all the header files and everything is being expanded, and that will go to compiler. .s file will be generated and that .s file will go through assembler. So object files are generated. All the object file will be now linked with the libraries using the linker, and then ELF, executable linkable format, that file will be generated which can directly be loaded by the loader into the RAM or physical address physical head address space so that the operation will be performed. So this is what happened, how we generate the from C source code to the executable. This is a simple example to add two values. Now when we simply compile gcc add.c -o add, we will get our ELF file. How we know that add is an ELF file? When we check, see, file add, this is an ELF 64-bit linked with all the libraries, build IDs corresponding to this interpreter. It is dynamically linked, all information we get. Now what happens between these, between the source file into the ELF? What are all the intermediate files which get generated? I'm just showing it. We have multiple files. How many new files will are created? ISO. So when you say ISO, C file we already have, I from the after the preprocessor, after the compiler S, after the linker O, after the loader we have ELF file. So all these files get generated, right? Let me show you what is in .i. .i after the preprocessor means whole header files get expanded and everything is expansion. So this is such a huge file. When you see the size of this file, see, size is such a large size compared to r.c, that is 91, this is 21316 bytes. Now what is .s? It will assembly code. So .s, complete assembly code. File is this, text section will be going to read only data, and we have a string which will, we have a global function main will be called, starting branch calls, allocating the memory, moving into the registers, doing the add operation, moving back into BS registers, moving into EAX, calling the main functions, calling the printf, and leaving the return statements, size, entity, everything. So this is the assembly code. .o is the will not be readable, it is, and then the ELF file. ELF is a structure binary format which can easily be understood by the machine. Okay, so this is what all happens when you write a C program and how the executable will be called. 3 intermediate steps is happening inside that, and each step has a detailed descriptions. Detailed understanding of each step is needed. So when we say at the preprocessor level, we are expanding all the headers and doing the micro substitutions, whereas compilation to assembly language, we can say all the assembly level coding we are seeing at the object file. Is the machine code object file, and at the linking level libraries has all been linked, and runtime startup code has been set, and and it got generated the ELF file. So now the next topic is why operating system. We have Linux kernel, Windows kernel, embedded firmwares, all are eventually using C. So why kernel needs C? First is direct memory access. C provide hardware control. We have a highly efficient interrupt handling inside C, and portable performance predictable. That is the reason we are using C. When we say that C gives a direct memory access or hardware control, I will just give you a simple example of this. So volatile, this is a keyword which tells the compiler not to optimize this value and read the value from the cache always. Unsigned int data type, we have a pointer variable to port where we have stored one address, typecast it unsigned int. This is an hardware register address. So we have mapped directly hardware register inside our code, and we on now we can simply do operations or this registers by changing the value, like we have 1 to the port, so we are directly changing this register. So it is like we are controlling hardware from software, controlling hardware. So it is like memory mapped IO. Input output registers are mapped into memory, so we are calling memory mapped IOs, or we are using addresses as hardware interface. This is hardware address, so we are using directly that. Okay, I hope this point is clear. Performance and predictability. Modern language, it means many things is hidden. First benefit is garbage collectors, runtime VMs, hidden allocation, and dynamic dispatch. So modern languages, most of the thing is being taken care by the operating system or by the interpreters itself. Programmer don't have to worry much. Whereas C gives lots of benefits and lots of responsibilities as well to the programmer. So in the C we have minimal abstractions, no hidden runtime cost, memory control, hardware control. So when we are saying tiny runtime, no hidden runtime cost, what it mean by? The program can run without operating system, without heap it can run, without file system it can run. It is the reason, as C doesn't need any operating system, heap, file system, C is dominating for the microcontrollers. C is dominating embedded devices, bootloaders, firmwares, and this is the reason, no hidden runtime cost. So like when I give you example, while one infinite loop, it is bare metal programming without anything. C builds the world. All the high level languages ultimately uses the C as their infrastructure. So C Python interpreter is C, databases SQLs and SQLite infrastructure is C. So C is the infrastructure language for other languages. Let me give you, we are saying that C is directly giving the memory control. Let me give you one example to show you the memory reality inside C. This is a very simple example where we have declared a variable x and assigned a value 10 to it. Printed the address and the value corresponding to that address. So this is address and this is value. From where this address is coming on, why this address is in this particular range 7FFE, this range, what is the mean of this range, how we can know that we are getting the memory allocated in the stack space, or what are the different memory spaces we have available, is it the virtual address or the physical address, what kind of address it is. If it is the virtual address, how the value we are reading from the actual hardwares. All these details has been covered in our memory thinking series. For example, let me show you from where this address is coming. ps-ef to see the processes currently running. We have this process running with the PID 2282. So cat /proc file system gives the live live internals of our process. So our process ID is 2282. We need to check the memory. So see the memory. We are getting address in 7FFE480 range, right? 7FFE480. So this address range is coming from the stack segment of the process address space. This memory ranges and this all detail is our process virtual address space, where the memories, where the segments has been mapped. So These memory range where our ELF is been back. Stack where is our ELF? This is marked at this address range 56176. Heap is a memory segment which is marked at this address range into virtual address space memory layout. We have .so shared libraries mapped. Similarly, we have linkers and loaders mapped. And we have declared our variable into a stack segment, local variable. So we are getting the memory from the stack segment range. And having the permission, read write permission, private. And these all are the inodes and major and minor number and this. So this is where we are getting the memory from the kernel. So kernel is exposing its memory space into us. Now let me show you, let me tweak this program. We have just declared a variable x without assigning any value. Let us show what the output we are getting it. Recompiled it, and why this is the random value. This memory range, as it is 7F, it seems that we are getting from the stack segment only. But when we are printing the value, we are getting some garbage output or some output which is not known by the programmer. Why compiler is not stopping us? We know that C trusts the programmer. It's the programmer's responsibility to write the code in an efficient way, to use the memories, to use the registers, assigning, deassigning, allocating, freeing, everything is the programmer responsibility. Programmer has the complete control over the memory. So C is just trusting the programmer. That trust sometimes leads to undefined behaviors as well. We will have a look into this undefined behavior in our we have a dedicated episode on this undefined behavior and other problems we face in the C in this series only. Stay tuned. So we have seen C is not only portable assembly, a very old language or merely a syntax, but C is a system interface language, hardware abstraction layer. It is the one compiler target language or infrastructure foundation. You can say that most language helps you forget the machine. C teaches you how the machine actually works. That's all in this episode. In the next episode, we are going to cover binary, hex, and computers number, how the data is being represented inside the machine, inside the operating system. Stay tuned for same. Thank you.